So hello everyone, this is our today's question. This one is a tricky question. I will tell you this question in simple words. Okay, so first solve by yourself, then come back to the solution. Uh, this question is usually for finding pole and zero in the MOS circuit. So this is a NMOS between sorry PMOS. This is a PMOS. So for solving, we can see there is a one capacitor connected between input and output node. This is output. To solve this, first we can uh, we can uh, we can distribute or split this capacitor into two by using Miller theorem. What Miller theorem say? If there is any gain circuit called A, and if there is a resistance connected between input and output node in the gain circuit, we can this is an impedance between, we can split this impedance in two parts, like this is a gain and this one is connected to the ground and this one also connected to the ground. Let's suppose z1 and z2. What is the value of z1? Z1 value is impedance z upon 1 minus a this gain is this gain. Okay, and what is z2? Z2 is the z impedance upon 1 minus 1 upon a. So this is our splitting impedance. So first let me make the circuit here. Now for the poles, this is for the poles. First we are finding poles. So cos poles is the simpler one. To finding pole, uh, let me make it clear. To finding pole, we are first finding poles. We will make circuit again. This is our PMOS, and this is connected to the ground and resistance, and this is capacitor CL, and there is one other capacitor. I will denote this as C double dash, and due to this splitting capacitance of CC. And what is the input side? Input side has this resistance and this capacitance CX, which is connected to the ground. As this node is connected to the ground, so I am representing this CX uh, as this, as here, as below. So another capacitance, I am denoted this as C dash, and this is Rx and V. Before solving things, whenever before solving this, I will tell something. I will tell this here, like if this is a normal MOSFET circuit and this is V in, or we can add resistance here as well, V in, or if there is no if there is uh, this is V out. If there is no capacitor like CX, C, and loading capacitance, then we can see this as what we can say, it is a steady state circuit. Steady state circuit. At steady state uh, capacitor shorts. No, it's not steady state. What we can say, capacitor open. So it's a steady state circuit. Capacitor steady state, and call as, we can call this as DC gain, DC gain as well as DC gain. Capacitors open, so there is no capacitance here, there is no capacitance here as well, as S is equals to 0. So impedance 1 upon SC will become infinite, and there is no capacitance as well here. So this is normal gain circuit, we can say. So the gain of this DC gain of the circuit is minus GM, or what is this, RL. And if we consider channel length modulation, this is the R naught of the output impedance of the MOSFET. So it is R naught parallel R naught, RL parallel R naught. Okay. For timing, I am not considering R naught here. And I am neglecting channel length modulation. So till minus GM RL, and this is gain. Okay. So this is our DC gain. So now we can find out this C dash and C double dash, as C double dash is as C dash is Z. And what is Z for this CC, which is 1 upon SCC and 1 minus A. AV is minus GMRL, which will become minus GM R and A plus GMRL. So this is C dash, and C dash is equivalent to CC 1 plus GMRL. I think you will understand what I did here, as this is considered as whole capacitance. So C dash is this capacitance. And what about this C double dash? C double dash is 1 upon SC 1 plus 1 upon GM RL. Okay, so this is our C dash, uh, which is equivalent to C 1 plus C, it is CC 1 plus GM RL. So this is for the capacitance. Now we know about C dash and C double dash. Now I'm giving you the important point for finding poles in this kind of circuit. To find pole, always consider these nodes. Like if there is a node, like this is one node and this is two node, always consider these nodes. At the number of nodes, at number of nodes where a resistance and capacitance are present, that number of node is that number of nodes uh, uh, that number of nodes tell us about number of poles. Like if there is two number of nodes, then we can say there is two poles there. If each node contains resistance and capacitors. Are you getting my point? Like I will explain again. If in these kind of circuits where MOSFET, when we have to find out the poles for the MOSFET circuit, always consider that node where resistance and capacitance are present. Like at that node there is one resistance and some capacitance, and in this node there is one capacitance, one resistance and some capacitance. This is RN. So the number of nodes represent that number of poles. Okay, if there is two number of nodes, we can say there is two number of poles. And if there is three number poles, we can say there is three number of nodes, we can say there is three number of poles. Consider the only condition here is that at each node there is one resistance connected. There is one resistance and one capacitance are connected, are equivalent and equivalent, we can say. Okay, so each node we have to see that if there is resistance and capacitance there, then we can say a pole is there. And if not, like if there is a capacitance here, and so we can consider this node as well, but we can see that there is no resistance here. There is no resistance here, so we cannot say we cannot say a pole is there. Okay, as this R in this R parallel to C is infinite. So if we find out the pole, then pole frequency will become zero. So we can say there is no pole. Okay, we can't say the pole is at origin. It is wrong. Okay, so always find number of nodes. Then we can say the number of nodes it's equal to the number of poles. This is our intuition. Okay, so for this pole I am denoting this as 1, and this pole I am denoting as 2. So pole number 1. So pole frequency we can consider as R equivalent and C equivalent. Rn. What is R equivalent for pole 1? R equivalent is Rx, and C equivalent is the combination of these two capacitors. As these two capacitors are in parallel, so I am writing here directly that Rx and this is Cx plus what is C dash is C dash this CC 1 plus GM RL. So this is our left hand pole frequency. Okay, this is omega p1. This is our first pole frequency. And to find the second pole frequency omega p2, we have to consider the R equivalent and C equivalent. And for the R equivalent, we can I'm changing my pen. So this is R. Okay, but there is one another R which is R out of the MOSFET, which is R naught. But we didn't consider channel length modulation. Channel length modulation is 0. So R naught is infinite, as R naught will depend upon 1 upon lambda ID. So lambda is 0, so R naught is 0. So currently R naught is infinite, so there is only one resistance which is RL. So 1 upon RL, and what is the equivalent? The equivalent is C C uh sorry, this is equivalent is C double dash and this C, and what is this C? This C is CL. This is CL. So our final pole frequency is this CC 1 plus GM RL plus mm, plus C plus CL. Now we can this RL, we can write this RL as here. Now 1 and GM is something small quantity, and this is let's solve it, then we will get to the conclusion. RL which is CC, and this is GM RL plus 1 GMRL plus A. Now we can say that GMRL is much greater than 1. So GMRL is much greater than 1. So it will simplify to this RL CC, which it will cancel out as the GMRL much greater than 1. So it will eventually become GMRL, and it will cancel out and will give up CL. Okay, so this is our final pole frequency, which is omega p2 1 upon RL CC plus CL. This is our pole frequency 2. Second pole frequency. This is our first pole frequency. This is our second pole frequency. Now uh, now this is for poles. Now we will gonna find out zero. So for zero, uh, now we will find out zero. For zero, for zero, V out to be zero. Okay, so in this we can see two conditions, like to become V out to zero. V out to be zero, this whole impedance to goes to zero. If V out is zero, means this whole impedance goes to zero. Uh, this impedance goes to zero, capacitance impedance goes to zero. As this will not goes to zero, a capacitance impedance will goes to zero, and when capacitance impedance goes to zero, this is 1 upon SC when S is infinite. So we can it is tell this this says that 0 at infinite location, but it can't be possible. 0 can't be at infinite location. So this condition is wrong. Okay. There is one another condition, like I will explain here by making circuit. This is capacitor. Sorry, this is MOSFET, and this is our circuit, and uh, this is our CC capacitor, and this is V in, and I will denote this voltage as Vx, and there is one other capacitor. This is not our point of interest currently for zeros, and this is RL and CL capacitance, and this is V out. When V out is zero, when there is no current in this branch, if I out is zero, if I out to zero, then we can say that V out is zero, as no current will flow to zero, no flow to this branch. So as no current flow to this branch, the V out will become zero, as this is the parallel combination of R and parallel combination CL, which is I out. So if I out is zero, that then V out is zero. To make I out zero, uh, there is there is one current flowing from source to drain of this MOSFET. So all this current which is flowing from source to drain will flow to this node from this branch. from uh, this path to this path. Uh, mm, we can say no current will flow, means no current will flow in this branch. All the current which are flowing from source to drain will source to drain follow this path. Okay. So if the all current if all the current from flowing from source to drain are goes to this path, then no current flow through this impedance. So our I out is zero. So we can say V out is zero. To now to consider this now to solve this, let there is one small signal current flowing almost from drain to source, which is in this direction, and this small signal current is GMVE, and V in is Vx as by GM VGS. And what is VGS? VGS is GM Vx. And why I am considering why I am considering Vs potential to zero as V out is zero, because I out is zero, so no current flow through this impedance, so V out is zero. So we can say that Vs node at zero. That's why Vs is zero. So this small signal current is GMVx, and uh, our main current are flowing source to drain, which is in this direction. So our small signal current is negative of this direction, negative of this current. So all this current flows to this branch, and all this current flows to this branch, as a small signal current is in small signal current which is GMVx is in this direction. Okay, forward direction. And one other another current is flowing in this direction, which is Vx, which is Vx. What can we say? Which is Vx uh, Vxs Cc. Okay, as this is Vx, and uh, this is impedance one open SC, and this current which is flowing in this direction is equals to minus GM Vx. Okay, if minus GM Vx, if we cancel out Vx, then S, which will become minus GM Cc, minus GM Cc. So the location of zero is GM Cc. We can say, we can say GMCC, and this is a right hand pole zero. This is right hand pole zero. So this is for the solution. As I am explaining this again, as uh, let me make here. This is our uh, this is our MOSFET, and this is our capacitor circuit. This is CX, and we have to make this current I out. Our I out is zero, so our V out will become zero. So there is one current flowing in this direction, as I am explaining in KCL term. So what is this current? This current is VXS CX. Okay, this is VXX, not CX. This is CC. Plus now there is one another current which are flowing from source to drain. Source to drain. And this is our small signal current. The small signal current is GM GMVx, and the summation of these two current is equal to zero. So if we solve, then we will get omega sz location is minus gm minus gmv minus gmvx. So minus gmc minus gmcc. So this is our final solution. I hope you like it. If you have some doubt, then ask in comment section.